partial derivatives and multiple partial derivatives and so on, and we're going to go through some of this list here. We need that. I'm picking this one because it's weird. It doesn't look particularly weird, but it is. We're going to do both partial derivatives for the function x to the power of ey. And I've written a little note here to remind you that there is a big difference between x squared and 2 to the x. If you differentiate x squared, isn't it just the power rule, right? Multiply by the power, reduce it by 1, so you get 2x. On the other hand, if you differentiate 2 to the x, isn't it this funny 2 to the x times the natural log of 2? So bear that in mind when we come to do this one. So first one I'm going to do is the partial derivative with respect to x. So what I can see here is really similar to this guy, right? It's x to the power of a number. So differentiate it, you multiply by the power and you reduce the power by 1. But you could, it's a pretty weird looking answer, but that is the answer, right? With respect to x, the partial derivative is 8y, x to the power of 8y take away 1. So far, so good. Now, this one is the one I think is going to cause the trouble. X to the 8y. It's much more like this guy, because really that is a fixed value. So that's like 2 to the power of 8y, right? So when you differentiate x to the 8y, you get x to the 8y times the natural log of what? What goes there? X. If it was 2 to the 8y, it'd be log 2 there. But we're actually not finished because there's a little baby chain rule going on here. If it was just x to the y, right? If I was just differentiating x to the y, the answer would have been x to the y times the natural log of x. That would have been totally correct. But it isn't x to the y, isn't it x to the 8y? So it's a chain rule. And don't we have to then differentiate 8y with respect to y, which means you get an extra 8. So 8 natural log of x, x to the 8y. Are you comfortable about that weird answer, right? Y is what it is. So let's move on to multiple derivatives, and not just the notation of them, but a guy called Clairaut who's going to be helpful. If you are finding, say, second partial derivatives, what you're doing here is you're differentiating twice, but you don't necessarily use the same variable each time. For instance, this one here means you differentiate the function first with respect to x, and then the second time you differentiate it, y is now the variable. On the other hand, this would be, you take this function z, whatever it's equal to, and you do a y, followed by y again. And those are pretty, I think, explanatory. Now, what Clairaut does is he says that you can actually switch the order. And so one of the versions of Clairaut says that this partial derivative and that one will be equal to each other, provided the function that you're using is a continuous function. Right, a nice smooth function, right? No weird vertical asymptotes or anything weird. So provided that, and we're going to make the assumption that every function that we're dealing with is continuous, so we don't need to worry about that. Now, if I went and said to you as a second derivative, that guy, that's how you would write it. Which one of those two do you do first? And which one of them is second? Because in this order up here, you do x first and y second. And if you wrote it this way, you would be telling people to do y first and then x second. What is the dy? The first thing you do or the second thing you do? Because this notation's, yeah. You remember we talked about this is kind of clunky, it kind of back to front, but that's what it is. So if you see this, you take the function f, differentiate it with y, and then that answer you then differentiate with x. The good news is that Clairaut saves your butt, because see if you did it the wrong way around, wouldn't you still get the correct answer? Because x and y, y and x. Now that it's a lifesaver, but just to remind you, that's what we mean, you know, when you write it in this format. So let's pick a function and pick a nice easy one to start with. Let's do a function, do a polynomial, x cubed, xy squared plus y cubed. And let's say that you're being asked to find that. So you do the partial derivative with respect to x, which is 3x squared. You differentiate this with respect to x, you get y squared. And you differentiate this, you get nothing. And then you do yx. And if you, sorry, you do y next, and you get nothing out of that, and you get 2y. So that guy is 2y. And isn't because of Clairaut, that guy also 2y. So if you're doing questions where they ask you to do both of these, can't you save yourself a little bit of work by just doing the first one and then writing the same answer for the second one, right? Because very often they'd say to you, find this fella, find this fella, find this fella, and finish with that one. In this case, wouldn't you write 2y here and here, right? And if you wanted to do an xx, wouldn't you take this fella and differentiate them, partial derivative with respect to x, and that would get you 6x. And if you wanted to do the y one, I guess I'd need to do an fy first. That would be nothing, that would be 2xy, and that would be 3y squared. And so if I wanted to do an fyy, that would be a 2x, and that would be a 6y. Have you noticed that those two guys are very different and typically will be? But these two will always be the same. Now, sometimes you can use Clairaut, which basically says you can do partial derivatives in any order you like, as long as the function is continuous. And you can do it to make your life much easier. Suppose I gave you that ugly function, and I asked you to do that. Right, that's the only one I wanted, right? When you look at that, would you say to yourself, I could do the same thing, but in a more efficient order? Would you agree trying to differentiate this with respect to x would be a pain in the butt, right? It'd be really, really messy, right? When you have to do a product rule inside a chain rule, and actually there's another chain rule inside that chain rule, right? Totally messy. But you don't need to, because can't you do that? Let's see why that would work better. If you differentiate this expression with respect to y, what does all this get you? With respect to y, what's this? Big fat 0. And so don't you only get 3y squared? Oh, let's put a y there, just so it doesn't disappear, plus an x squared. And then you can do with respect to x, and that gets you nothing, and boom. Do you see how simple it was to get that second derivative by changing the order in which you do them? Right. So just because you're being asked to find x first and y second, doesn't mean you're forced to do it that way. Can't you choose whichever order you think is going to make your calculation simple? So I think that's kind of a nice little added benefit to Clairaut's theorem. I'll show you another thing you can do when you're doing multiple derivatives, and that is called symmetry. If you're lucky, you will get a function that is symmetric. Here is an example of a symmetric function. Now, a symmetric function is one that if the x and y swapped places, you would still have the same expression. Now, if I switch places on this, it would be y squared plus x squared over 2yx plus 4. But with a little rearranging, isn't that the same thing as the guy you started with? Great. So that's what symmetric is. Now, if someone asks you, and I'm not going to do it because it takes too long, but asks you to find the partial derivative with respect to x, you're going to have to fight through some horrible quotient rule. And I'm pretending I know the answer, which I don't. Can we just pretend that the answer ends up being this thing here? Right, just for argument's sake, right? Once I have fought my way through this answer, because it has symmetry, I can actually do the other derivative without redoing the whole question. Don't you just take this answer and replace the x's with y's, right? Switch places. So what we would get is a 3y plus a y squared over 2xy plus 4 squared. Let's pretend, again, I'm pretending I know the answer. Let's pretend I did the hard way, because I'd have to this guy. And it ends up being 3xy plus x cubed over 2xy plus 4 to the power of 4, right? Suppose I fought my way through and I found this one. Because the function is symmetric, shouldn't I also be able to find the second derivative with the y's without redoing the entire calculation? Any volunteers for it? What if this is correct? What would that one be equal to?
Three yx plus y cubed. 2yx plus 4 raised to the 4th power.
Doesn't that half your workload? Because you only really need to do one of them the hard way and then use symmetry to get the other version. And you already do that. Doesn't Clairaut say that zxy and zyx is the same? But symmetry is a little bit better than that. Doesn't symmetry say that if you know zx, you can also figure out zy? Clairaut doesn't, right? Clairaut, the first derivative with x and the first derivative of y are very often totally different from each other. But when they're symmetric, aren't they very essentially the same as each other? Structurally, at least. Any questions about Clairaut or symmetry? They're really helpful to reduce your workload. Any questions? We're good? Okay. Let's move on my little list. The basic we're going to get us to nowhere. We've done a lot of these before, so I guess I could maybe pick one last one. What one will I pick? Let's pick 14. It's the last one of that type of question. So V is going to equal the sine of 3s squared take away 2t squared. So that function is not symmetric. So I'm going to have to do these questions the hard way. So I'm just going to pick a couple. Let's do VSS, that's one of the ones. And let's do VT. Right, I'll do VT since it's a single partial derivative. Sine of this ugly guy is cosine of ugly guy. It's essentially a chain rule. So once you've done the cosine of this, you then differentiate the inside function with respect to t. which gets me negative 4t, because that's worth nothing. And then you make it look slightly pretty. And there's our partial derivative with respect to t. Okay, now this one. First, I have to do the first partial derivative with respect to s. Differentiate the sign of something, you get the cosine of it, times the derivative of the inside function, which just gets you 6s. Now, to do second partial derivative, also with s, I need to differentiate this. I hope you recognize this is going to be a product term. Can you see an S here and an S here, right? Two different locations. So I'm going to make these guys the F and this big ugly thing the G. So that's going to be product term. With respect to S, that gets you 6. Leave the other guy alone. Plus, leave the S alone, and then differentiate this guy. Well, that's going to get me negative the sign of 3s squared take away 2t times the derivative of the inside function, which is another 6s. So I get 6 cosines. This guy times this guy and a negative gets me negative 36s squared and a sine. We're done. Right, so if I give you any multivariate function, right, some function in 2, 3 variables kind of thing, do you feel comfortable about finding first derivatives? Second derivatives? Using Clairaut and or symmetry to maybe make your life a little bit easier as well, right? So if you recognize it's symmetric, you can save yourself a bit of work. If you want to use Clairaut, isn't it sometimes easier to do one order than the other, right? Do ST before you do TS, whatever it might be. In many cases, it isn't going to be of any great help to you, right? Because they're ugly no matter what order you do it, right? And that's okay. So next thing we're going to do is a version of question 19, where we have a very, it's almost like a historical equation. I mean, this is like.
Once you're done with that, could you go back to 16?
I certainly will. Thank you. But let's not do that yet then. While we're on the floor, let's do 16, because I did promise that one. So let's see what the heck's going on in 16. Oh, okay. So we have a function, and it's e to the power of x, y, z to the 7. And we're being asked to find the partial derivative, that guy. Okay, so I'm going to start by differentiating with respect to x. So that's e to this guy. Times the derivative of this guy, right? It's basically a chain rule. Now, with respect to x, don't you end up with the y, z to the 7. So far, so good. Now, differentiate this with respect to y. Well, that's going to be a bit messier. That's going to be f. This is going to be g. So I will need a product rule. And so if you differentiate this with respect to y, you get z to the 7. Leave that guy alone. You leave this guy alone. And then you differentiate g with respect to y. So you'll get e to the power times the power, right? The derivative of that power. So with respect to y, the derivative of that is x z to the 7. So I now have this fella plus that times that, yikes, plus an x, y, z to the 14, e to the power of x, y, z to the 7. So far, so good. Right, I really don't like this question because it doesn't have any shortcuts to it. It's just ugly. Essentially, won't I have to find both of these with respect to z? So if I want to do this one, won't I have to do a product rule? And on this one, won't I have to also do a product rule? So I have two distinctly different product rules. Now, the person who asked to do this, was it just, it looked like it was just becoming a monster and you must have done it wrong because it was just growing and growing and growing. Is that what your issue was? Or
No, right there is where I messed up. I didn't do a product rule plus a product rule plus a product rule plus a product rule. I tried F and G at one side and F and G the other side. That was it. Basically one product rule. They didn't combine them.
And it didn't end well.
Yeah, no, it didn't.
Okay, so do I need to continue this? Because it's going to take me a bit of time.
No, I understand it now.
Right. So, I mean, you've still got another 5 minutes work by the way, guys, right? You know, there's a whole load of messy bits. And I'm looking at the answer right now, and it looks about that on my screen. So I know it's massive. Have fun. That's all I'm going to say. So let's return to that puzzle on 19. That's true about anybody. If you're doing homework or you've came across a question that you think isn't making sense to you, it very often is going to help other people because it won't make sense to them either. Right. Right. Here we have an equation that's called, I think it's called Laplace's equation. Let me check. Yes, it's called Laplace's equation. And it's used in wave theory, I believe, and heat flow. So if you can find a function where this partial derivative equation is true, right? So the second derivative with respect to x plus the second derivative with respect to y equals 0, you've got a solution to what's called Laplace's equation. And evidently these are kind of cool things to know. And they give you a big list of equations to test. The one I'm looking at has 6. So I'm going to pick this one first. Hey, maybe that'll work, right? Let's take it up. If you differentiate it with respect to x, you get that. If you do the second derivative with respect to x, you get 2. If you take the original function with y, you get 2y. And if you do the second again with y, you get 2. But that plus that is 2 plus 2, and it doesn't equal 0. So that's not a solution to the Laplace equation. So far, so good. Now let's pick one that works. I've got them in front of me, so it makes my life 10 times easier than it is to get. I have the natural log of the square root of x squared plus y squared. And this one works according to what I've got in front of me. And I need to find its second derivative and in terms of x, and then its second derivative in terms of y. And allegedly, if you add these two things together, it works. Okay, but I'm not going to do that. I'm going to do that. Why do you think I converted this log of a square root into a half log? Because they are equal to each other. But why do you think I did it? I'm lazy. Isn't it easier to differentiate the half log than it is to differentiate a log of a square root? Isn't that a chain rule inside some other chain rule? And by the way, remember, we're going to have to do a second derivative on this, right? So you don't want to do anything that's going to make your life a misery. So if you do the partial derivative with respect to x, a half log x gets you a half, 1 over the thing, times the derivative with respect to x of the inside function. And the derivative with respect to x is 2x. And that cancels. So it looks like I'm going to get x over x squared plus y squared. Now, if I want to do the second derivative with respect to x, call that f, call that g. I'm going to do a quotient rule. So it's going to be f dash g, take away f of g dashed, all over g squared. So it's going to be 1 times x squared plus y squared, take away x times the derivative of the bottom with respect to x, 2x, and the whole thing on the bottom is going to be x squared plus y squared squared. And that's going to get me an x squared, take away 2x squared, and that's going to give me a y squared. So after a little bit of tidying up, not much, but after a little, you're going to get that. Are we okay with the, let me get my screen, it seems to be in the wrong place. That helped. There. Can you see the guy there? Right. Are we comfortable about that being the answer? Right. Now, is this function symmetric? So shouldn't I be able to just write down what that is equal to without actually working it from scratch? Don't you basically, the x's and y's switch places? So it's going to be x squared, take away y squared. Now, technically speaking, wouldn't that be y squared plus x squared, all squared? But isn't that the same thing as x squared plus y squared, all squared, right? Just to make it look. Now, what's going to happen when you add these two together? Aren't they going to cancel each other out? And that means that they add up to 0. And isn't that what we're looking for? Functions who have the property that these two add up to 0. And so this would be a solution to the Laplace equation. As far as I can tell, there are 4 right answers and 2 wrong answers. So good luck. Any questions so far? No? That's scary. Are you sure there's no questions? Okay, I'm cool. Here is a little side issue. Still on partial derivatives. Normally when you, I'm going to use Z all the time. If someone gave you that guy to do, right? You would normally be asked to find those 2 first partial derivatives, right? That's kind of a standard question. Now, when a function is written in this format, right, the variable z equals a function of x and y, it's just a normal explicit equation. Now, sometimes The equation looks like that. Now, do you notice the only difference is that it's not z equals, it's z squared equals, right? It might be the next time sine z equals, or cosine z equals, or e to the z equals. When you have an equation where all three variables, including the major one, in fact, we even have names for these two guys here, the one on the right-hand side, they're called the independent variables. And this fella here, the one that everybody uses the formula with, is called the dependent variable. Every function that we've dealt with so far has always been f equals, z equals, right? P equals, right? So it's been pretty easy to deal with because these are the two variables and this is the one that you are typically going to differentiate. When they look like this, this is called an implicit function. Can you remember back in Calc 1 doing x squared plus y squared equals 9 and finding differentiating those things? Remember that implicit differentiation thing, right? This is like the grown-up version of that. This is like the big version of that same concept. What we have to do here is change how we look at some of the variables. So if I'm being asked, as you will be, to find the partial derivative of z with respect to x, x is a variable in terms of x. Isn't y treated as a constant? That's still true. But z is different. I want you to treat z as if it was a function of x, which it is actually, right? If I rewrote this, wouldn't z be the square root of this? And we're trying to avoid doing that, right? So you take each piece and you differentiate them with respect to x. So this guy here becomes 2z dz by dx. Does that look an awful lot like differentiating y squared in Calc 1? Right? 2y dy by dx, isn't it? It's got that same kind of look to it. Now, differentiate that, you get 2x, and differentiate that guy, you get nothing. And so isn't dz by dx 2x over 2z, which actually becomes, because you can simplify, x over z. And that's okay. The answer is allowed to have z. And we call that implicit differentiation. Give you another example. What do you think that might look like in 3D space? It looks something that you've seen before, but just a little different as well. What do you think that would be in a 3D space world?
Is it a sphere?
Yes, it's actually the surface of the thing, right? Everything on the outside. Now, you want to do a partial derivative of this. Because the x, y's, and z's are essentially jumbled up, you use implicit differentiation. So if you're being asked to find dz by dx, differentiate this with respect to x, differentiate this with respect to x, and differentiate this with respect to x. Get that. And differentiate this with respect to x. And now you have 2z dz by dx, 2x equals 0. And then the next few lines are basically solving for dz by dx. So as long as you do it to both sides, it's okay row. So the first thing I'm going to do to both sides is subtract my 2x. And then I'm going to divide both sides by 2z. And looks like we're going to get an answer very similar to the one I just did a minute ago. And there is the derivative with respect to x. Is this function symmetric? Right? So shouldn't I be able to figure out, oops, what dz by dy is equal to. Agree? What do you think the partial derivative dz dy is?
Negative y over z.
And boom, you're done. So this is a special situation, isn't it? This is how do you find first partial derivatives when the function that you're given is not z equals, but some z squared, z cubed sine of z. In fact, now I thought of, I should probably do one more. How about this fella here? That's a pretty ugly looking function, isn't it? And suppose you were being asked to find the partial derivative of z with respect to x. Now, I could, and I'm not going to, I could jump right into using this process, but I'm going to do one extra line of algebra. Always, what's that rule I use? Yeah, just because you can doesn't mean you should draw, right? I could do that right now without doing, just figure out what that derivative is, figure out that, and off I go. But I'm not. Isn't the inverse sine of z squared the same thing as saying z squared equals the sine of that? You agree algebraically? Wouldn't that be much easier to do implicit differentiation with? So you're always going to try and say to yourself, can I do this easier, right? Well, z squared seems to be my go-to guy today. So you differentiate that, you get 2z dz by dx. You differentiate this with respect to x, you get a cosine times the derivative of the inside function with respect to x, which is 2. And the z by dx then is 2 lots of this cosine divided by 2z. The 2's cancel out, and so you're left with a very nice, I think, a very nice answer. You agree that was pretty smooth? Now, if I had stuck to my guns and did this one using implicit differentiation, I would have got the correct answer. But here's a weird thing. It wouldn't look like this answer. It would have inverse cosines in it and square roots of 1 minus z squares and a whole load of other weird stuff, right? And it's not that it's wrong. Analogy. Do you know how in trig you can have 2 answers that are totally different, but because they have trig functions in them, they're really the same thing, right? It's that kind of analogy. Not only is that going to be harder to do, I bet you the answer when you're finished will look a lot uglier than this pretty answer. And so there are benefits to doing implicit differentiation. I think we're good now. Are we good? Right. Almost forgot that section. So we're now moving on to a little bit more stuff. Oh, I just noticed something. Let me show you what I just noticed. It's not a biggie, but it's such a good question, I don't want to kill it. But it has the hyperbolic sine function in it, and you don't know what the hyperbolic sine function is, do you? Yeah. Right. Now, I'll show you the guy I'm talking about. It's sometimes called cosh in the science. I can't even say it, but that's what they're sometimes called. Can you see this guy up here? Sine x, hyperbolic cosine y, cosine x, hyperbolic sine y. Do you see that funny little h next to it? They're called the hyperbolic trig functions. They're kind of interesting. They are created or understood from Taylor series. Remember doing Taylor series of sines and cosines? No, you don't, because you haven't reached it. I just realised that's a Calc 3 thing. You will eventually do Taylor series of sines and cosines. And when you do, you'll find out that the hyperbolic sine and cosine functions are essentially very closely connected to the sines. So this is the only thing you need to know. When you differentiate a sine, don't you get a cosine? When you differentiate a hypersine, you get a hypercosine. Okay, so the derivative of sine hx is cosine hx. Isn't that nice that it's not that weird? If you differentiate the cosine of x, isn't the answer negative sine x? You remember that? Differentiate a cosine, you get a negative sine x. What do you think you get if you differentiate a hyper cosine? Cosine h. You've got 50-50 guess on that. I'll tell you. You got a positive hypersine. The darn thing doesn't work the same way. Do you notice that they're both positives? If you differentiate a sine h, you get a cosine h. If you differentiate a cosine h, you get a sine h. Isn't that totally back to front and upside down? They're almost positive. So if you remember that, you can do question 90. Right, we're now moving on to our next section, which is 14.5. And again, we have done some of this, quite a lot of this, but not all of it. 14.5 is a chain rule. The chain rule is how to do partial derivatives, or at least derivatives, of functions when the variables, the x's and y's, are themselves in terms of another variable. So the only one I've got time for today, and we'll continue this tomorrow, is this situation. So suppose z is equal to x squared plus 5xy. And suppose x is t squared and y is 4t plus 1. Right? So what we have is z is a function of x and y, but x and y are themselves functions of time. And so this type of situation happens when you've got a surface in 3D that is changing through time. So you can imagine it would be a flowing hill, but 1 second later the hills went higher and the valleys went lower. It's like analogy. Can you imagine trying to model waves in a sea? Right? The waves don't stay put. Don't the waves move to the left or the right? And don't they sometimes get higher and lower? And doesn't that change through time? So if you were wanting to model something like that, this is the way you would do it. Now, if you want to find the partial derivative of these guys, and I just said partial when I shouldn't, if you want to find the derivative of this guy, the only question that you're likely to be asked is find dz by dt. Right? And it's a proper derivative. And the reason why it's a proper derivative is, couldn't you turn everything into all the x's and y's into t's and just differentiate the old-fashioned way? But the formula for it is the partial derivative of z with respect to x times dx by dt plus the partial derivative of z with respect to y dy by dt. So think about this as being the contribution to the answer made from the x's, and this is the contribution to the answer made by the y's. So if you differentiate this with respect to x, you get 2x plus 5y. And then if you differentiate this with respect to t, you get 2t. And then you go back and you now differentiate with respect to y, and that gets us 5x. And then the derivative with respect to t gets me 4. And so this thing looks like 2xt 10yt plus 20x. What we have is the derivative of z with respect to t. Now, do you see that it's a mixture of x, y, and t's? That's pretty common. Now, WebAssign has got issues sometimes. I think it's pretty generous with these ones. What does that mean by that? It'll allow you to write all these guys down. In other words, this is the right answer. It might, just might, sometimes expect you to do a little bit more. So if you get an answer and you're sure it's correct, but WebAssign doesn't like it, the reason it doesn't like it is it wanted the answer only have t's in it. So instead of 2x, it's 2t squared times t. Instead of 10yt, it's 10 4t plus 1 times t. And instead of 20x, it's now 20 t squared. You see, I've just replaced everything in terms of t. And then you tidy it up. So that's 2t cubed, 40t squared, 10t, and another 20t squared. So I'll turn that into 60. And that would be your answer. I'm pretty sure that answer is acceptable almost all the time. But just in case it decides to be awkward, you remember for these questions, that's just the ones where the x's and y's are in terms of a single variable t, that you might have to turn your answer into nothing but t's. Yeah.
Last semester when we did this in Calc 3, only the first one that had to do that.
Right, so it's pretty rare. So they're comfortable with that? Is that what you're saying, David? Is that what you remember?
Yeah.
Yeah,
Only
that's great.
once
That's what I would
last
like. Yeah. So maybe one question where you had to do this, but most of the time they were happy to leave the x's and y's, which is good, right? It makes your life simpler if you can get away with this version. Right. You remember, only put your last name down for attendance. And as soon as you've done that, bye-bye.